Hello friends, welcome to the next lecture on cache memory. Today our point of discussion is on the performance of cache memory, right? So essentially we all know that whatever we do, we are concerned about the performance of that system, right? So that plays an important role. And for today's discussion, we'll be following. You can follow any of the books, both by Hennessy and Peterson, either the usual one or the appendix of this one, a quantitative approach, right? Okay. Now, this is a known diagram to you, popularly known as memory hierarchy diagram, and this is already known to you, right? And the excess time of these memory devices or other memory units increases this if you traverse this way. Now what we are interested, basically, see what we have a computer, right? And for us now, the computer is not, we won't say a simple computer, we'll say, well, it consists of CPU, memory, right, and IO devices, right? So for us, it's a computer system nowadays. If you enlarge CPU, we'll have data path, and the efficient version of data path is being done by pipelining and others. So for us, a system is of this fashion now, right? Now what do we have? We have this system, and what happens, what is the purpose of using these systems? Essentially a program, right? An application, be it, let's say, your a game, or this any application, any word application, or whatever, any application you can think of, in your system. Now eventually an application, as we know, it's essentially a program, or then a running instance of a program. We call it a process, right? Or rather, put it in another way, this will contain a set of instructions, and we are supposed to execute these instructions in this computer. So essentially it means the CPU will execute these instructions. These instructions will be stored in memory, right? It will read instructions after instructions from memory, and it will execute it. And eventually, from a user's perspective, we will see that, okay, the application is getting executed, right? Now what we are interested, being a user, we want that how fast my application can run, right? As simple as that. कितना जल्दी में एग्जीक्यूट हो सकता है, राइट? तो कितना कम हमें वेट करना पड़ेगा, so right? So that is one of the important characteristics, or one of the important parameter from user's perspective, right? There are various other parameters from systems perspective, from the manufacturer's perspective, right? Like the cost, and of course from the system's perspective, it might be energy consumption and others, right? And where people are putting more attention in the topics like that, energy consumption and others. So for us as a beginner, we will concentrate on the access time. So we want to understand how this placement of this cache memory in this stack helps us to either to reduce the overall time, and by how much, right? So that thing is particularly will be handled by the topic of today's discussion, is called the performance, right? Okay. Now with this background, let us go, and as you mentioned, So let us go to a deeper thing in performance. See, we can say that execution time of a program, right? So by execution time, we meant the CPU time eventually. So it can be, it can be thought of comprising this CPU execution time, right? कितना time execute होने में लगेगा वो instruction, right? The components inside the CPU will take to execute that particular set of instructions, and how much time it has to wait for the memory, right? As we know that if you go to the type of the instruction, or other the parts of the execution of an instruction, we'll see that it consists of fetch, decode, and then actual execution or ALU, right? Then followed by memory and write back. And for these places we need to go to the memory, right? And we can assume that, and these are happening inside my CPU. So for one instruction it happens to be time for this plus this plus this plus this plus this, right? The stages, right? Eventually we can say that the whole time will be dependent on the memory access time, right, and the CPU time, CPU execution time, right? Okay, now if that is the case, we'll place some of the results or some of the formulas what we have already seen when we discussed the CPU performance. Now today we'll add the memory performance with that, right? And as a whole we'll see the performance. Now see, these are known to you. What is that? The cycle, or rather you come here to the second equation, CPU time. If you know the number of cycles, then you can simply multiply it with the clock cycle time or divide it by frequency. We have already seen this particular formula while we discussed CPU performance. Now just over here we told that the CPU time will be consisting of the CPU execution time and the memory stall time, right? So I'll put it in terms of cycle. We can say it is CPU execution cycle plus the memory stall cycle, right? Once we get the cycle, we can multiply it with the time so as to get the actual time, right? Okay, now if that is the case, what will be the memory stall cycle? How will you find out memory stall cycle? Now for that, let us go to the board. Yeah, so as we know that CPU runs a program consists of instructions, right? These are instructions. Okay, now if you are given the instruction count, then you can look, or you can try to find the cycle time per instruction, and you can multiply it with the instruction count, right? And that is popularly known as CPI, you know that, right? Cycles per instruction. Now if you have a memory system in place, right, so how will you do? We are interested to find when we'll go to memory, right? So you will not go to memory always. So in a sense that the memory, by this memory we are meaning that the CPU will check in the cache, let's say, right? If it is found, then we say that it is not a stall, right? It is getting the things immediately, so it's not a stall. We don't need to wait for that. Now if we need to go to the next level of memory, let's say main memory, then only we'll say it's a stall, right? And now come here, So when you go to the next level of memory, so that will depend on the misses, right? So as we know that number of misses per instruction, right, that happens to be the multiply by 100, that happens to be miss rate. So that miss rate will be the memory stall cycle will be driven by the miss rate. Miss rate जितना ज़्यादा होगा उतना ज़्यादा जाना पड़ेगा, right? And if you multiply it with the cycle to serve that miss, right? So here miss, what do you mean by serving a miss? Serving miss is essentially to bring the things from next level of memory. Next level, right? That's what is called serving a miss, and this is popularly known as miss penalty. We have already seen the term in the first lecture. Miss penalty, to bring block from next level or the main memory to the cache. Now, how much cycle you incur as a miss penalty, right? And that you can multiply with the miss rate so as to get the total memory stalls per total memory stalls for the whole program, right? And yeah, so this can also be written as this: cycles to solve the miss is essentially miss penalty. So for us, for a program, the memory stall cycle happens to be the instruction count. IC means instruction count. Instruction count multiplied by the miss rate multiplied by the miss penalty, right? So this will give us the memory stall cycle. If you get the memory stall cycle, suppose you are given the CPU stall cycles also, then we can find out what will be the total number of cycles, right? So that's what we'll be doing in this problem. Look at the problem. Assume the miss rate of an instruction cache. So I hope you have seen, in the pipelining, that there will be two types of caches will be used. For the fetch, we'll be using, instruction cache, and for the memory, we'll be using data cache, right? And this was used so as to avoid one type of hazard, structural hazard, if you remember that. Well, now you are given the miss rate of an instruction cache as 2%, and the miss rate for the data cache happens to be 4%, right? And a processor has a CPI of cycle per instruction of 2 cycle without any memory stalls, and you are also given the miss penalty. Now the question is, what will be the memory stall cycle for the instruction and as well as for the data cache? So we are given that memory stall instruction cache will be having 2% of miss. So if that is the case, we can say that memory stall for instructions is for the whole program rather, so the instruction count, we assume that IC happens to be the total number of instructions for the program, 2%, right? So 0.02 multiplied by, this is miss penalty, right? So this happens to be 2 into IC, right? Similarly, we can find out the memory stall cycle for the data, right? So this happens to be, now it is given that 36% are the load and store. So as you know that in MIPS processor, the load and store is responsible, for the memory operations. So it is given 36%. Now if we have total instruction count as IC, so IC into 0.36 happens to be the percentage for the memory operations. And for this data, right? So as you know, this again the load store will happen at the mem stage of our pipeline, this m stage. Now for this data cache, we are given 4%. So then the memory stall for the data segment happens to be my 1.44 into IC. It's a simple multiplication, right? So these two are giving me memory stall cycle for the cache, right? Instruction cache and data cache, right? Now for the whole CPU time, what will be this? Yeah, so this is the total memory. Yeah, total memory cycle happens to be, because instruction will be, this phase will be for all the instructions, and the next one will be for only load and store type of instruction, right? Okay, now this happens to be the total number of memory stall cycle happens to be this. Now what will be the CPU execution time? This happens to be the, you are given, in case of ideal scenario, CPI is 2, so that means this, for CPU purpose we are spending 2 cycles per instruction, so that 2 plus 3.44 happens to be 5.44 into instruction count happens to be same, and let us say cycle time, CPU cycle time is given as cycle time, so that is the CPU execution time. Now you are supposed to find, what is the question? Determine how much faster a processor would run, right, with respect to a perfect cache. So this is a normal cache with this, the given credentials. So this happens to be the CPU time. But in case of perfect cache, is already given that the CPI, so perfect cache means everything will be hit, right? So that's what perfect cache means. So if everything is hit, we assume that it is assumed to be inside my my CPU, so no memory stalls. So that means it is the instruction count into my CPI into cycle time, right? Now at one end we have this, at the other end we have this. Now what is the difference? Or rather, what is the factor? The factor happens to be 5.54, into IC into cycle time divided by 2 into IC into cycle time, which happens to be 5.44 by 2. So it means with respect to the perfect cache is 2.72 times faster with respect to the scenario given, right? So in this example deals with the overall execution of a program with some instruction count and with some CPIs and the miss rate of instruction cache, data cache having them in place. Now the point is, you can see that it is a factor of 2.72, even if the perfect cache would run 2.72 times faster, even if the the miss rate were only 2% and 4%, so it's not much, right? Even if we are incurring only 2% and 4% misses, it is other way around, it is 2.72 times slower, right? Okay, now moving ahead with our discussion. We are introducing a term called average memory access time, right? So what does it mean? So this means so program, again come to the program, a program will have several instructions, right? These are instructions, INSTR, right? Now all the instructions are not of same type, we know that, right? And we have seen that thing in details in a topic called addressing mode, right? Now, even if in case of a base, simpler instruction set architecture called MIPS, all the instructions will not take same amount of time or same amount of cycle. Why? Because few instructions will not involve, if you write the stages as 1, 2, 3, 4, 5, typical five stage instruction or pipeline. So this will be taken by all. Let's say, this will be taken by all. This will be may not be by all. This is of course not by all. This may not be by all, right? Anyway, so you can see every instruction is taking, or rather different instructions might take different amount of cycle. Now, even if in case of memory, so this happens to be involves memory, so not this one. So this involves memory because it's a fetch. This involves memory. Now, even if things are, memory is involved, things will not take same amount of time, right? How this whole thing will be, more clear when we'll in your OS course, because we can see that, there you'll see that to get one particular thing from main memory, you might need to access the main memory a couple of times, maybe once or twice, right? So based on that, this time varies, right? But for us, if you recall that, let's say if you use indirect memory or indirect addressing, right? Now we can see that in indirect addressing, the memory access happens to be twice memory access happens to be twice. Just a minute. So memory access happens to be twice so as to get a particular thing. So essentially what you want to say is that for few instruction it might take, let's say, some x cycle for memory access. For few it might take some y cycle, right? For few it might take some z cycle. So number of cycles incurred for memory access is not same throughout the instructions. So we need a better way to estimate that, right? So a better way is what happens. I'm sorry, I'm getting some issue over here. Yeah, so we are here eventually. Just give me one more minute. Let us disconnect this, otherwise it will make some problem. Yeah. Okay. So we were here that instructions will take different amount of memory cycles, so we need a better way to express that, and the better way is this average memory access time, so which happens to be heat time plus miss rate into miss penalty. Now the question is how this is coming, right? Now we see that to understand that, let us come here. Yeah. Now you remember the cache, the flow chart of cache execution. So here is the CPU generates request to the cache. Is the cache, right? And we have our main memory, or next level of memory, right? So for this discussion, we assume that next level is the main memory. So CPU will ask for some data, right? And so it will be searched in the cache, right? That's first request. Now it is searched in the cache. If it is there, it will be returned, right? As simple as that. Now, if it is not there, then what will do? It will eventually come here. So then it will be seen that okay, it is not there, right? Then it goes to the next level. Then we assume that things will be there in the next level, right? And it will bring the things here. And then it will be delivered to CPU, right? Now see how many times it will take this path, two path, जितने बार miss होगा, है ना? So that means it is essentially, it's not the whole thing, it is depending on the miss rate, right? Now coming so coming here, searching and giving a word is called heat time, we know that, right? And coming here and bringing the things is called miss penalty, right? So that means you will anyway, either you take the 2 or you take 4, right? These are same. So you come here, 1 is anyway common, you search the cache, right? And then you give the result to the CPU, right? So all the time you are executing this portion. How much time you need to execute this portion? What is the time? The time is heat. How much time? What percentage? 100%. Always, right? So that means it will be heat time. Now how much time we are doing this part, the second part? जितने मिस रेट होगा, राइट? एक मिस रेट सर्व करने के लिए कितना चाहिए, और रादर वन मिस सर्व करने के लिए कितना चाहिए? मिस पेनल्टी अमाउंट चाहिए, जितने भी है कुछ, दैट विल बी आइदर साइकिल और टाइम, राइट? सो वी मल्टीप्लाई दैट. So then this happens to be the average, on an average for a program, right? Will be, we need to incur this much amount of time as far as memory access is concerned, right? So this happens to be the heat time plus miss rate into miss penalty, right? Okay, so as it is said that it will be measured either in absolute time or in CPU clock cycle, right? Then we will be solving two problems with that. So that thing we're coming in the let's say next part of